And then there's the intrinsic function, being able to understand how to use that intrinsic function. That's the right intrinsic function, right?
We use interp.
Yeah, it's interp 1. That's what I called my function. So the the intrinsic function is interp 1, and then you also used interp 2 in the pre-lab. So understanding how that function works, which actually we wrote our function to work exactly the same as the intrinsic function. And then the last piece is being able to write the algorithm. So for interpolation, the algorithm has a couple pieces. The first piece is the window algorithm, which locates the bracketing points. And so a lot of you have gotten started on this or finished this algorithm, and it's just a find function, or a find algorithm, which we've written several different kinds of. And then the last piece is that you have to nest 2 for loops within one another. One of the for loops will go through your x star values, and the other for loop goes through your x values to find the window. And I think this is the first time we've done this double nested for loop. So just thinking about how that might work to have 2 nested inside each other. So there's that. And then I've noticed, I've noticed that there's 2 misconceptions that I've seen in a lot of people's codes that I want to make sure that it doesn't happen to you again. So first is for loops. I don't know how many times me and the TAs have noticed that people are writing the syntax for loops this wrong way at the bottom, where it says I equals the length of x. That runs the loop for 1 time. And it's not actually totally crazy that you would think that, because other programming languages use that syntax. They just say run the loop 20 times. So I equals 20, run it 20 times. But that's not how MATLAB works. MATLAB runs the loop for every element in the array. So I equals 1 colon length of x, 1 colon 20. It's going to run for 1 and 2 and 3 and 4 and 5. So make sure that you're not doing that, because especially with the sum function, we noticed it a lot. Then the second thing is functions. That was supposed to say call me, not all me. I don't know why I didn't notice that. So I think functions are starting to make sense to a lot of you. I'm starting to see connections made, but there's still some confusion about how functions work. So remember that when you write a function, you can choose 0, 1, or many inputs, 0, 1, or many outputs. And the way that you write the function is with the function declaration line and an end, and all the code goes in between. There's a whole other thing about how that's stored in a file if you're going to put multiple functions, which I think you guys are starting to get now with all the quizzes. But then when you call the function, what you're doing is you're giving the function specific things for the way that you wrote it generally. So this is generally written for any x, y, and then I'm calling it for 2 and 3 specifically. And we're going to do this every single time we write a code, this writing it in general and then calling it many times. And then the last thing is, if you ever use an intrinsic function, you can't just like, oh, I'll just try this. We'll see if it works when I put these inputs in. You have to look up in the help or in Google how the function works with outputs and inputs. There's no other way to use intrinsic functions. So if you have to use one on a quiz, on an assignment, anywhere, you're required to be able to know how to look that up. That's the only way that you can use it. I personally treat Google with a lot of respect, and I actually do phrase all of my Google searches as questions. People tell me not to, I can't stop. So if I have a question, I write it in the form of a question. And so my friends always make fun of me that I'm like writing Google a letter every time that I'm Googling. Like I'm like, dear Google, could you please tell me about, and it is very similar to how I do it, but you can Google however you want, you know, most people use. Those are my tips. I hope and I feel that functions and loops, they're starting to make sense. You think so? Do you agree? The more you use them, the more it's like, okay, got it. I was just kind of like pretending I knew and I was putting in all the syntax, but now it's actually making sense. Uh-oh, did I just unplug this? Oh, I just unplugged it. Okay. All right, so today we're starting topic 10, which is integration and differentiation. So we're doing everything computationally, so we're looking at how to computationally integrate and differentiate. This is by far my favorite topic because I'm a modeler, and so that's all I do pretty much is integrate and differentiate equations. So this leads you into 303 really well because you're going to start solving differential equations, both ODEs and PDEs in 303, which are exclusively based off of this. And then when you move on to finite element method or computational fluid dynamics, it's just worse. It's just more of this. So, you know, think about it. And the prereq for this class is just Calc 2, so that's why we stop at integrals and derivatives, because that's all you guys have done with your calc classes, or that's the only requirement. But we look at this in a couple different ways. So the first thing that we start working with in this topic is the symbolic toolbox. And this, we don't use any toolboxes in this class aside from this one. And in other classes, like not the computational classes, but in like in a circuits class or even a fluids class or maybe in a controls class, you'll use all these toolboxes developed for MATLAB, which usually have GUIs. Do you guys know what a GUI is? A graphical user interface, so you don't usually see the code, you're just like pushing the buttons, but they're all written in MATLAB code. GUI, it's G-U-I, and you say it GUI. Yeah, it's not a word, it's an acronym. So, so this is the only toolbox that we use, and it's pretty much all command-line toolbox. It only comes with the student version, so if you buy the professional version, none of the toolboxes come with it. You have to pay for them each separately, but you should all have access to the student to this toolbox, with the exception of if you purchased a previous version of MATLAB, like last year if you purchased it because it wasn't free for students, then and you only purchased the $50 version, it's not going to have this toolbox in it. The $100 student version has all the toolboxes with it. So what it is it's a tool basically to do all the stuff you're doing in calc, but it does it for you. So if you've ever used Mathematica, it's very similar. It's like an analytic toolbox that can like differentiate analytic equations, integrate analytic equations. It can do algebra for you. It can do everything. So it's actually a really nice tool to be familiar with just for comparing for working on calc homework. Then we're going to cover numerical derivatives, which are called numerical finite differentiation, and numerical integrals. So we're going to think, okay, we understand the continuous or analytic form of calculus, the derivatives and the integrals. So how could we let a computer do that? So remember, computers are dumb. All they can do is say 0 or 1. You know, they read binary, they write binary, they just do binary, right? So you need to convert everything that us genius humans can do, like calculus, into something that a computer can do. Computers can do algebra, but they can't do calculus. Isn't that sad? So you have to convert the calculus to algebra for the computer, and that's what we're doing today, is understanding that connection. So the symbolic toolbox is what I'm going to start with. God, that was just my overview. I talked way too much about just what I'm going to talk about. Okay, so I'm just going to go over some syntax for the symbolic toolbox, and you're going to do a lot of this in your pre-lab. So I'm going to move over to MATLAB and show you just some quick syntax with this, and then hopefully that's enough to kind of get you started. So the symbolic toolbox requires you to basically distinguish a variable as a symbolic variable. So the syntax is SYMS and then a space, and then any variable you put in is going to be called symbolic. So you can see when it comes up in the workspace, you see how it has SYM in there. It's not just a value like what we're used to if we defined it equal to 1. So that says X is symbolic. And then you can write X in any equation, and anything you set it equal to on the left-hand side is also now going to be symbolic. So now I've created a symbolic equation that's the sign of X. And then there's all of these different functions you can call on that use symbolic variables. So the first one is diff. Diff is how you take a derivative symbolically. So you can see that when you do diff of f, it just differentiates analytically, like it's giving you the analytic differentiation of cosine. And I know I just told you that MATLAB doesn't do calculus, or computers don't do calculus, but this is all programmed in. It's all just like a bunch of memory that has what's the derivative of sine of x? Look here. You know, it's not doing it. It doesn't know it. You know, it's all just programmed in. Does that even make sense? Anyway, then for integral, it's f. Or it's int, sorry, int, f takes the integral, and then there's additional inputs that you can provide. And some of this doesn't make sense probably quite yet with where many of you are in calculus, but you know, you can have multivariable functions that depend on multiple variables. So you could also not only integrate f, but you could integrate f and tell it which way you would like to integrate it with respect to x, y, z, and then you can also plug in numbers. So you can integrate f from 0 to pi or something, and it will give you the value when those bounds are plugged in. And I'm just showing you the very basics. You'll do a lot more in your pre-lab to explore that a little bit more, but that at least gets you started with how it works. So the key is that you need to define a symbolic variable to start using the symbolic toolbox. Is there any questions about the symbolic toolbox? All right, and then we're going to move on now to 2 and 3, starting to look at numerical differentiation and integration. Okay, so let's just talk for a second about the difference between having discrete data and continuous data. So MATLAB, for example, it only works with data, aside from the symbolic toolbox, which means that it only operates on arrays of discrete points. And MATLAB is a dumb computer language. It can only do exactly what you tell it. It can't make decisions. It can't decide on whether things are okay or not. All it can do is exactly what you tell it to do. Where mathematics which is what we're trying to have MATLAB be able to do, it's all communicated through these analytic functions and relationships. And all of the functions are continuous. They don't have points associated with them. And mathematics is really, really smart and very, very difficult. And it's designed by humans. It's our interpretation. I actually will get way too philosophical with this, but you know what I mean? It's like, it's just something someone made up to explain something else. You know what I mean? It's like a language. So somehow in this section, your job is to connect these. Luckily, you don't have to figure out how to do that. Someone already did. And that's what I'm about to show you. See ya. Okay, so we're going to start with the derivatives. Actually, I'm going to start a new page because I'm going to make a little table for you guys. Sorry, I can keep this here. So, why is everyone leaving? Something going on? Okay, see you later. Something happened? Everyone's like, something's wrong in here, gotta go. So I'm going to show you several different types of differentiation, different methods. And so I'm going to show you the name of the type, and that's sort of like what's used in numerical methods community, like what the name of it is. I'm going to describe it. I'm going to provide you the equations. This is kind of like what you need to do in MATLAB. And then I'm also going to show it to you in a plot example so you can kind of visualize it. So the first type of derivative is called a forward difference. I feel like I skipped a page. Maybe that's a good thing because I do not have time. Definitely skipped an entire page. Sorry for those of you who are going to be upset with this. I think I need to just explain this really quick before I start the table. So let me just explain to you in a bigger picture what this is. So okay, so finite difference is a derivative using discrete points, okay? So let's say that you have a set of data that we've looked at lots of data points like this. So I think everyone knows that if you have a continuous function, you know that the derivative of this function is just the slope at any point on the function line, right? And so if you remember back to the fundamental theorem of calculus, if you take any x location and then go h distance away from that x location, you can define the derivative as the difference in the delta y, the slope rise over run, over the difference in the x, which would be h. And as long as the distance between those 2 points approaches 0 or is really, really small, this is exactly the derivative. Okay, do you guys remember the fundamental theorem of calculus? Okay, so in numerics, we're going to do the same thing. We're going to use that same philosophy, but we're going to look at it with points. So here is a set of discrete points. And I'm just going to grab onto 2 points and I'm going to label them generally. So I'm going to call this point here x of I, just because it's just the same as choosing any point, but you could think of this as x2, this is x3, this is x4, so in general, any point xi. And then I'm going to get the point next to it, and the notation we use for this is x of I plus 1, just meaning it's the point immediately to the right of it. And those have associated with them function values, the y coordinate, so f of I and f of I plus 1. And so if you want to numerically calculate the derivative at I, you just do the same thing. You take the rise, which would be f of I plus 1 minus f of I, and divide it by the run, which is the delta x, which would be x of I plus 1 minus x of I. And oftentimes our data is evenly spaced, so if every x is like evenly spaced from the next x, so x of I plus 1 minus x of I is always the same. So a lot of times you'll see these formulas written with h's in them because h is always the same between every 2 points. So you'll see that a lot. So what we just did is we took a continuous idea of a derivative or a slope and we converted it into a difference. So derivatives are equivalent to differences. They are numerically, their equivalent. So here we were calculating the slope at this point and we used the point in front of it. And so that's why it's called a forward difference, because it's using the point in front of it. But as you can imagine, you could use any point surrounding it. There's a lot of different ways you could do it. So what I wanted to show you is a couple different ways you could do this. So the first way is the one that I just showed you, which is a forward difference. And it's called that because it uses the next point. And the formula is the one that I just showed you. And so if you want to just look at 3 points, I'm going to use the same 3 points for all these examples. And I call this point I. This is the next point, I plus 1, and this is the previous point, I minus 1. If I was estimating the slope using a forward difference, the slope would look like this. It would use those 2 points, and that would be the slope. Now, if I use the point behind it, the slope would be different, right? It would be a different slope. So that's a decision that you make as when you're doing these numerical methods, is which point you're using. So that leads us to a backwards difference, which is going to use the previous point. So if you're calculating the derivative at I, you're going to take the point itself, I, and subtract off the point behind it. And so if I draw the same 3 points, I minus 1, and I plus 1, the slope is going to look like this. And remember, the slope is just it's a scalar value that throws people off a lot. So at every point, you can calculate a scalar slope that's associated with the derivative at that point. So who has an idea of something we could do better than a backward or a forward? Yeah, an average, a central. Use both. So central differences use both neighboring points. So if you're calculating the derivative at point I, you are going to use both the point in front of it, and you're going to subtract off the point behind it. So it spans 2 grid cells. So instead of dividing by h, a central difference would divide by 2h because it's going through 2 spots. So here, the slope would look like this. So a central difference doesn't use the point itself. It only uses the neighboring points. So there's a couple things that are important to realize with these differences. The first is that central is most accurate. It's using two pieces of information from your function or from your data, so it's better. It's going to have higher accuracy. But each point is only using one other point. So all the points get used to calculate the slope at all the different points, but each point's only using one point. What was your question?
I was saying like that forward backwards to use like xi plus 1, xi.
They use 2 points, but they use the point that it's at and one other point.
I was just saying 2 new pieces.
Yeah, so basically what the central is it's an average of the two. If you average these two slopes, you'll get a central difference. So you're actually using two different differences to get the central. So that's why it's more accurate. So I have a question for you. Why do you need the other two then? Does anyone have any ideas of why you would ever have a one-sided difference?
You want to find the slope of the first point and the last point?
Yeah, so on your boundaries you can't do central derivatives, right? That's not possible. You're trying to get points that don't exist. So on your boundary points you're forced to do one-sided differences. So in your lab 10, you're going to be differentiating data from a Tour de France race. And so I think you have the elevation profile and you're going to calculate the vertical speed. And so you want to calculate the speed at all points. So you're going to need to employ all three of these differences as needed. Any questions about that? Any questions? Okay. All right, so moving on to integration. It's easy, right? It's just differences. Like it makes it easier because when you numerically differentiate, you just subtract, and we all know how to do that. So let me first just define an analytic integral so you have some notation. So I is my integral when I integrate f of x over x from x equals a to x equals b. So everyone is familiar with that. So if this is my a and this is my b, what does the integral represent in this plot? The area under the curve. So an area under the curve is equivalent to a sum. So derivatives become differences, subtraction. Integrals become sums. And you guys can sum. You just did it, right? Everyone can sum in MATLAB. So this algorithm is very easy. So if you want to write the integral in its differential form, you're going to break your domain up into, so let's say I had just discrete points on that same function that I wrote up before. And let's say I wanted to calculate again from A to B. If I wanted to do this, I would first need to break down that area into rectangles. So I'm going to take this point and I'm going to make a rectangle. I'm going to take this point and I'm going to make a rectangle, this point and make a rectangle. And if I do enough rectangles, I'm filling out the entire area approximately with a bunch of rectangles. And I'm going to call each of these different integrals. And if I sum those integrals, I'm going to get the total integral. Now, how do you actually calculate this area? Well, you know the spacing is h, right? And you know that the height is its function value. So you can easily approximate that area in a million different ways by just taking some width and multiplying it by some function value. Now, how you choose those is what makes up the different integrals. Now, the biggest misconception about integrals is that when people write these integral algorithms, they basically just take the entire width from b minus a and multiply it by one function value. That is a very horrible way to approximate an integral of data because it's going to be very much not right. You need to break it up into however many points you have and approximate as many rectangles as you can and then sum them up. And I think that's really the most difficult part about this is kind of thinking about how that works. So let's write out some of the different methods that you can do this. And what's interesting is most of you should have seen this. I'm like losing track of schooling, but you did this sometime in high school. The midpoint rule, the left-hand rule. I don't know when, because it wasn't in calculus, right? It was something else. Was it in calculus? Yeah, Riemann sums. So you were like, oh, this fundamental theorem of calculus crap, why are they teaching us that? And they're like, Riemann sums, like, why would you ever approximate an integral or a rectangle with the left-hand rule? And now you're like, wow. They're amazing, those teachers that I had. They taught me that. Because honestly, like as complicated as like computational fluid dynamics sounds or finite element sounds, like this is all it's doing, you know, like honestly. All it's doing is sums and differences. And once you can wrap your head around that, the sky's the limit for you. So rectangular rule is the most simple way to break up these rectangles. And there's two ways you can do it, the left or the right hand rule. So you can either choose to use the left point or the right point. Numerically, all it is each integral will be defined based off of the h spacing and the function value. And so if the function value is the left, you just have to make sure that I index is choosing that left point. And if it's the right, then you have to make sure it's choosing the right point. And the thing I want to make sure that you remember is that this is only finding, like let's say you wanted to find the integral over some entire a, like AB. You wanted to find the integral over the entire domain. This is only defining what it is at one interval. So let's say that you have a point here. The points are evenly spaced here. This would just say that the first integral, which would be this rectangle here, is going to be based off of the first function value. So this would be I of 1 because it's using f of 1, and then we would call this h of 1. And then the next time it's going to use this point, the second point, as its function value to approximate the rectangle. And so you would just keep going through and doing each one. The next one is the midpoint rule. This one is actually probably the most confusing to think about because what it's actually doing is it's using a function value and then multiplying it by the width of the 2 points on either side. So if I do the same plot here, the midpoint rule would only be able to calculate the rectangle right here, and it would use the width on either side. Then it would calculate it right here. Didn't pick a really good function for this. but it has to use 2 points because it doesn't, you can't actually just pick the middle of 2 points because you wouldn't know the function value at that point. So you have to span 2 points for the midpoint rule in order to do the, otherwise you'd have to interpolate to get the point in between. And the last one, which is the one you're programming in Lab 10, is the trapezoidal rule. It is the simplest one that is the easiest to program, so it's the most often used. And if you have fine enough data, then it's usually good enough. So that's why we use it. And trapezoidal rule is one improvement to the top two in that instead of just taking the midpoint, it takes the average of the 2 points. So again, if I have some function, it's actually going to connect the 2 points with a straight line, and the area will look like a trapezoid. So the area is so much more accurate than chopping off the corners like the other 3 methods do. So that's what it visually looks like. So in this, we don't talk about accuracy in this class at all. That's something you'll talk about in 303 a lot, like understanding how to actually determine accuracy. But I hope you can just believe me that trapezoid is the most accurate method. And in your lab, remember, you need to make sure that you're not just solving for the integral over one interval. So you see here how I wrote, this is the numerical integration over a single, this should say interval. You need to find the numerical integration over all the integrals, all the intervals. So you're going to have to take all those I subscript i's and you're going to have to sum them up. So step 1 is to find out what they are, and step 2 is to sum them up. So you can create a loop to define each one, or you can even make a more sophisticated algorithm and determine how many times each point is used in general, and you can actually do the whole code in one line. Or the whole algorithm in one line. So I'll let you kind of think about that. Can I just say that I've noticed a lot of people are like looking on the internet for these formulas like correlation coefficient, interpolation, these formulas. Just why don't you just look at the notes? Like it's going to be so much harder for you to figure out if it's the same equation. They're not always written the same. The algorithms are sometimes different, and you're just setting yourself up for a lot of struggle, especially on the exam. You have to use the formulas I gave you, especially for all the correlation stuff. So be careful about that. All right, that's it.